Hi, so we are continuing our discussion on ideal fluids. So in the previous discussion, we derived the ideal fluid equations. So we actually saw that the moment equations, so the continuity equation, momentum equation and energy equations, these three moment equations, they constitute a dynamical theory. I mean, three means one is vectorial, of course. So, well, I mean, if we count the number of scalar equations, we have 5 equations in total. So they constitute a dynamical theory finally when the system constituents, they follow a local Maxwellian distribution that we saw in the previous part. And the momentum evolution equation then simply becomes del V del T plus V dot nabla V is equal to minus gradient of P by rho, which is the gradient of pressure force, okay, so which is actually coming from the inside of the fluid. So that is not an external force, okay. So P is the fluid pressure basically. So it is coming due to the pressure of the fluid, and this is the external forcing agent. So I said that this is something which we call the body force, okay, and most of the cases in astrophysics this is either external gravitational field. In some cases it can be an electromagnetic field as well, but most of the cases this is a gravity, field of gravity, okay. So this is an equation of the acceleration, of course. Okay, so del V del T. So here you will see this is nothing but the density of force. Okay, so mass density of force. So basically this simply says that this is force per unit mass, which is acceleration. Okay. Now in this discussion, what we will do that till now we were talking about deriving or obtaining the fluid equation or the known equations for the fluids or the continuum, okay, starting from the very basic kinetic theory. So this is called the down to top approach, okay. So that means we are starting from a very basic level, quantum, then single particle, then kinetic, okay, the statistical level, and then finally a continuum level. Now it is also true that the these fluid equations can equally be obtained. So at least here till now we have talked about the perfect fluid or ideal fluid equation, okay. So that can also be obtained from macroscopic considerations. That means if we are just seeing from using such a length scale where we are not we don't have a microscopic view, we don't need a microscopic view, but we just see right from the beginning the fluid, as a continuum. So we cannot see with our acquired instruments or measurement method, we cannot see their constituents. Still we can obtain these equations. So basically that is the obtaining the macroscopic equations macroscopically, okay. So in most of the fluid mechanics books or in engineering books, the fluid equations are derived in that way. And actually historically people, when they derived them or obtained them, they actually did this macroscopically, and that was much more interesting. And then people who wanted to know that really this is consistent with our microscopic theory, or rather how can, starting from microscopic theory, we can really find a beautiful down to top approach, and just by saying that from microscopic to macroscopic, how we can develop the different levels of theory, a hierarchy of theory. So for that people tried this approach, what I was discussing, okay. But now let me do something which is very much conventional, okay. So let us just let us just try to reobtain, that's why I'm saying the word reobtain, those force terms which are in the force equations, okay, force terms from a macroscopic point of view. But before that, it is also useful to say that if we try to handle or study a fluid medium or a flow medium, okay, macroscopically, we need to know about two approaches which are equivalent, but they are a priori not the same approach. Okay, so one is called the Lagrangian approach, another is called the Eulerian approach. So in fluid mechanics, a flow in continuum can be studied in these two following ways. The first one is called the Lagrangian view. That means we just assume a very small fluid particle type of thing inside a blob of fluid in a flow. That will be, of course, an imaginary blob, because this is a continuum. You cannot find, you cannot think of a discrete particle like that. And this blob of fluid will be traced throughout the flow, and we will see that where it is going with time. Okay, so if we just trace this being on the blob, okay, so let us consider that we are the observer and we sit on that blob of fluid, okay, and we go at every point, and where we are going, we just measure our positions. And when we measure our position, taking the ddt of that position, we also measure our velocity. So in this way, we can measure the position and the velocity of the blob of the fluid. So this is the way one can study a flow, and this is called the Lagrangian view, okay, or Lagrangian approach. There is an approach, alternative approach, which is very, very useful for physicists at least, okay, and also for studying complex type of fluid flow where you cannot really trace efficiently fluid flow. For example, I have not talked, but let's say you have a chaotic flow or something, and where it is very, very difficult to search for a blob of fluid, okay. Then, because this is a mess inside the flow, it's highly non-linear and everything is like you cannot see layers. So there is a very, very high chance that once you start tracing a blob of fluid, you will be lost in some moments. Okay, this is highly possible. Then a very effective approach is the Eulerian approach. Okay, and this Eulerian approach simply says that you are the observer. Okay, again the same thing, we are the observer and we don't move, and we just sit or place ourselves inside at one point in the flow field, okay, and then we will measure the fluid which is coming and the passing that point, and we will measure the velocity of that particle, okay. This is one, so that is the thing where we are not changing our space, but we are simply measuring the velocities with respect, of different fluid particles. Okay, so here basically we are not interested in one single fluid particle, but we are interested in one point in space. Okay, so that is the part where you will see that how the velocity at one point just changes explicitly with respect to time, and that gives you that partial time derivative of velocity or any quantity. It can be a velocity, it can be density, it can be pressure. So whenever this fluid particle or some fluid passes through the point where you are sitting, you just measure its density, pressure, velocity like this. So basically finally when at some other time interval another fluid comes, so no change in space but only time is changing, okay. So that simply says that this will give you some partial time derivative of that corresponding quantity, okay. Again another thing is there, that is in the same way you can also do something that in the same so basically that is of course you can easily understand that is not all. So that is a partial picture of the studying the flow, okay. So now we can say that, okay, many of us, we are sitting at different point in space, and all of us are measuring, okay, all of us are measuring velocities at a given time instant, and that will give us an essence of a partial space derivative of velocity. Once again, when I just say velocity, that can be any property of the fluid, okay, velocity, density or something, I mean velocity, density or pressure, whatever, and that will be given by its, actually this is wrong, yeah, by is this variation, okay, and this is called the advective derivative, okay, of some quantity. It can be, once again, it can be rho, it can be velocity itself, okay. Now this is, so these two approaches are equivalent, and that's why basically a combination of these two parts of Eulerian approach, that means in one case you are not changing space but changing time, and in one case, so the study is being done at different point in space but at a given time, of course then more than one observers are needed, okay, the combined result will finally give us something. So basically I mean some particle which is coming here and at a given time instant, it will have some, I mean it will have some so if I just try to write, so let's say this blob, I am sorry, let's say I am interested in this blob, okay, I'm interested in this blob, and this blob is now I am just tracing its dv dt, okay. Now these dv dt can be obtained just by the combination of del v del t plus v dot nabla, okay. That is simply because d dt is nothing but del t plus I should write like this, sorry, d dt is nothing but del t plus del x del t, sorry, dx dt plus del x, sorry, del y dy dt plus del z dz dt, and this part is nothing but this advective derivative part, okay. So finally, due to the equivalence, you can see that this ddt is equal to del t plus v dot nabla, okay. In our derivation, we obtained what we did was, I mean starting from the kinetic theory, we obtained the Eulerian derivatives, of course, okay. Now these derivatives sometimes is called the material derivative or the total derivative, okay. So once again this is sometimes important when we are talking in terms of fluid particles, okay. Now let's look back to the equations of continuity and we will see, so these two approaches were important to be introduced just simply because these two are I mean the approaches to study fluid motions or a flow macroscopically, okay. So if the equation of continuity, you can see del rho del t plus v dot nabla rho plus rho times divergence of v is equal to 0, then this del rho del t plus v dot nabla rho is nothing but d rho dt by definition. This is a Lagrangian derivative, and that is equal to minus rho times divergence of v, okay. And now just so the basic, so that was just to tell you how the Lagrangian's derivative will look like, okay. So this was the Eulerian derivative, Eulerian time derivative, so this is the Lagrangian time derivative. Now just have a look at the force equations. So the force equation is written like this: del v del t plus v dot nabla v is equal to minus delta p by rho plus g. So what is this? This is nothing but dv dt. So this is the acceleration of a fluid particle, and finally you see that the total force or total force per unit mass which is acting on that fluid particle is given by the sum of these two terms. One comes from the inside, or one from is the internal of the fluid, that is the gradient of P by rho. Another comes from the external part. Okay, so finally we can say that we have something like a Newton's equation, but of course in density sense, because we are talking in terms of fluid flow. So rho times dv dt will be equal to minus gradient of P plus rho g. Okay, so this is a force equation if you want. Now we want to check. So this one we already got, but we have not derived it now, I mean till now, macroscopically. Now to obtain these equations from macroscopic considerations, we have to define two type of forces. One is called body force, another is surface force. Okay, and whenever we are talking about this body force and surface force, basically we have to we had to introduce this this concept of this fluid particle. Okay, whenever we are saying that the force is acting on something, then that something is given by the fluid blob or fluid particle, and then this Lagrangian derivative comes into play, and that's why I introduced basically this, both the Lagrangian and this Eulerian point of view. Eulerian is the one which we are using throughout. Okay. Now, what is body force? So, body force is something which acts at all points of the body of a fluid element. You see, we still use the notion of the fluid element. Okay, and so this is known as the body force, or the bulk force sometimes people say. So this is given by FB. Okay, so if we are just taking a fluid particle of, let's say, mass, elementary mass delta tau, small fluid particle, delta tau is the volume, so the mass will be rho times delta tau. Okay, so rho times delta tau, then the total force will be given by rho times delta tau times g, because g is nothing but the mass, force per unit mass, the body force per unit mass. Okay, and then what is the surface force? Okay, so this acts at all points of the body of a fluid element, so this will be proportional to the volume. And surface force is something, this acts across the surface enclosing the fluid element. So for body force, this acts at every point of the volume of the fluid element, and surface force acts across the surface enclosing the fluid element. So surface force basically acts over here. Okay, so that's then the surface force, the same thing, that some small incremental delta Fs surface force should be expected to be proportional to the incremental area, some small area delta A. Okay, and if this is proportional to delta A, then basically one can simply write that delta Fs is equal to, so when two vectors are proportional, of course, then the proportionality constant can be a scalar, or there is another possibility that both of them are joined by a tensor of rank 2, which is given by a matrix, right? And that is the general possibility, most general possibility, and that's what we are writing over here. So delta Fs will then be equal to some tensor of rank 2 P prime, which will be contracted to delta A. Okay, and then the total F is, so that will be some incremental or some infinitesimal surface force, of course. Now the total surface force will then be a surface integral over the whole surface. Okay, and if you now remember the famous Gauss's divergence theorem, then what is that? This is nothing but the closed surface integral P prime dot dA is nothing but volume integral divergence of P prime d tau. Okay, now you see, if you write this incremental total force is equal to incremental body force, or plus incremental surface force, then that will be simply written by rho g plus divergence of P prime times d tau. sorry, okay, P prime times d tau, okay. And this is basically, if you just simply identify your pressure term, this P prime term as, I mean, this new tensor to be minus of the pressure what we just introduced in our original definition, original derivation, then we simply get back our ideal fluid equation. Okay, that's simply that. Then this is actually, we know for ideal fluid, this is, I mean, this is minus divergence of P, and minus divergence of P is even simpler for Maxwellian case, for minus gradient of P. So we again get back our ideal fluid equation starting from macroscopic considerations. Once again, whenever we are talking macroscopic considerations, we start from fluid elements. Okay, and that is the reason why I introduced this Lagrangian point of view. Okay, now fluid element is the smallest entity of the macroscopic framework. Okay, so in the next part I will discuss the different properties of ideal fluid. Thank you very much.